My name is Adriana, and welcome one more year to SIMBa. So first of all, we would like to thank BGS Math for their support. Moreover, mention that this year the seminar will be organized by the students of UAB, UB, and UPC. The sessions will be held online every 2 weeks starting today at 12:20. And as you've seen today, at 12 we'll have like a little coffee break or tea break if you wish. And we'll try to do some social activities. Sometimes they might be also after the talk. So to receive all the future information, you can subscribe to our newsletter if you aren't already. We'll also have Twitter, and we'll be posting there as well, so you can go follow us there as well. In case it happened that you cannot attend some of the future sessions, we have YouTube channel. We'll be uploading all the sessions there whenever we have the consent of the speaker. And last but not least, if you consider giving a talk, or maybe if you know someone who would, all you have to do is to fill in the form you can find on our website. So if you have any further questions, do not hesitate to contact us, or yeah. And so now, before we move on to today's talk, we also have an attendant who is Adrian, who'd like to tell us something as well. So Adrian, please.
Yeah, hi, I don't want to take too much time. I think most of you already received this information, but I'm not sure. So I just wanted to tell you that we are organizing a conference which is bringing young mathematicians together. And this mainly is supposed to be to PhD students, but it also, I think it's interesting for master students. We will have very interesting workshops, very interesting plenary speakers. It can be an opportunity for you to present a talk or a poster. And the deadline for sending an abstract to present something, unfortunately, is this Sunday. But also, if you don't want to present something, you can just enroll yourself. It's completely free. And I will put the information in the chat, and then you can check everything carefully. And also, if you want to write me an email, I'm part of the scientific committee. So that was basically the conversion.
Thank you. I think now, Salvador, it's your time.
Okay. Before introducing Shehzad, I would like to ask all of you that while the presentation is going on, you turn off your cameras so not to overwhelm the system, and so Shehzad can have as smooth as a presentation as he can. And now I have the pleasure of introducing Shehzad Hathi. He is a Bachelor of Mathematics in Indian Institute of Technology in Kanpur. He also is a Algand alumni, having stayed for his first year in Padua and his second year in the University of Bordeaux. And currently he's pursuing a PhD in University of New South Wales, Canberra, in the topic of analytic number theory, advised by Professor Tim Trajan, I guess. I'm sorry. And before we start, I think we wanted to record this, and I would like to start the recording before I ask him about the image rights and so on.
Yeah, I've already started. So
okay, great. So now she said, I guess you will have to answer one very long question.
Sure.
That do you allow the seminar SIMBa to capture, reproduce, or adapt any of like your talk for the purpose of creation, preservation, or dissemination by SIMBa independently or joining with other materials of SIMBa of your talk? I don't know. This is very legal thing.
Yes, yes.
Okay, and do you allow this material to be publicly communicated and or distributed under the attribution non-commercial, no derivative works, Spain Creative Commons license or similar for the activities of SIMBa related to research, teaching, and training, including its YouTube channel?
Yes.
Okay, so you have the floor, sir.
Okay, thank you, Salvador, and thank you to all the organizers for inviting me and giving me this opportunity. I'll share my screen now. Yeah, okay. Is it visible to everyone?
Yep.
Salvador,
Yeah.
is it visible?
For me, it is.
Okay. Well, yeah, I hope it's visible. Yeah, so the talk is about the circle method and Linnik Goldbach problem. So I'll first start by introducing Goldbach conjecture. It's a famous unsolved problem, which states that every even integer greater than 2 can be written as the sum of 2 primes. So for example, 12 can be written as 5 plus 7. This variant of the Goldbach conjecture is also known as the strong Goldbach conjecture because there is a weaker form of it, which we'll get to in a minute. Sometimes it's also referred to as the binary Goldbach conjecture because we have 2 primes, so p1 plus p2 equal to n, where n is an even integer. So since you have 2 primes, it's called binary. The weak Goldbach conjecture is referred to as the ternary Goldbach conjecture as well sometimes. And obviously is an unsolved problem. Dates back to the 1700s, maybe even further, but at least the first recorded instance of this conjecture is from the 1700s. And there have been a few breakthroughs. So for example, in the 70s, Chen proved the result that every even integer greater than 2, so every sufficiently large even integer can be written as the sum of a prime and a semi-prime, where semi-prime is a number with less than or equal to 2 divisors. So it includes primes. It also includes a few other numbers apart from primes. And that proof was done using sieves. Chen introduced this double sieve, which has been used later in many instances, also in the case of Vinogradov conjecture. So the weak Goldbach conjecture is that every odd integer can be written as the sum of 3 primes. It's weak because if you have an odd integer and you subtract 3 from it, 3 is a prime. And if you subtract 3 from it, it will become an even integer. And then if you apply the strong Goldbach conjecture, it means that you can write every odd integer as a sum of 3 primes. So the strong Goldbach conjecture implies the weak Goldbach conjecture. And in this case, it's proven. In 2013, Harold Helfgott proved the weak Goldbach conjecture using the circle method. So circle method has been used in this instance. In general, the circle method is useful for ternary kind of problems compared to binary kind of problems where the sieve methods work better. We'll get to this. Right. And finally, the Hardy Littlewood conjecture. So it's a more precise formulation of the Goldbach conjecture. It says that the number of representations of an even integer as the sum of 2 primes is asymptotically equal to 2c0 times this product over primes p minus 1 over p minus 2 times this integral dt by log t log 2n minus t. And c0 is referred to as the twin prime constant. 2c0 is around 1.32. And it's referred to as the twin prime constant because, as I said earlier, there is some relationship between Goldbach conjecture and twin prime conjecture, and so this constant also occurs in the twin prime problem. So to introduce the circle method, here is the basic idea of the circle method. It's a well-known fact that the integral from 0 to 1 of e power 2 pi I n alpha is equal to 1 when n is equal to 0. and 0 when n is any other integer. It's also standard notation to write e power 2 pi I n alpha as e parenthesis n alpha, so that you can just remove 2 pi I. You don't have to write it every time. So now if you have s as a sequence of integers, let's say 1, 1, 0, 2, 3, whatever, any sequence of integers. And if you want to find the number of zeros in S, here is a very difficult way to do it, or a very fancy way to do it, so to say. What you do is you take the integral e from 0 to 1 e n alpha d alpha for every n in the sequence. And let's forget about whether the sum converges or not and those other issues. But you can conceivably do this sort of thing where you sum this integral over every integer in the sequence and you find out the number of zeros in the sequence. So now I'm going to use a trick, which is a standard trick in analytic number theory. And there is this joke by Bob Bourne, a famous analytic number theorist, that analytic number theorists basically just know 3 things. One is Holder's inequality, the other is Cauchy-Schwarz inequality, and the third is writing your quantity as a double sum and rearranging the summation sign. So I'm going to use that last trick here and rearrange the integral and the summation sign. So that's the basic idea. And you can do this rearrangement provided things are nice enough. But the cases that we are going to consider, things are going to be nice enough. So this is basic idea. And if you want to apply this to the circle method, to the binary Goldbach, then you write n as p1 plus p2. And this can be rewritten as p1 plus p2 minus n equal to 0. And so then we want to count the number of zeros of this equation, p1 plus p2 minus n, and let Rn be the number of representations of n as the sum of 2 primes. Then you can represent Rn in terms of this integral. And here the situation is symmetric in p1 and p2. So instead of writing p1 and p2, you can write s alpha equal to sum of e alpha p, and then we have s alpha squared in the integral. Right. And then the most important part of the circle method is this division of the unit interval 0, 1 into major arcs and minor arcs. All of these notations, all of these terminologies, sorry, not notations, but terminologies, they are for historical reasons, because the modern formulation of this method, major arcs and minor arcs are actually intervals, and 0 to 1 is also an interval, and basically the union of major arcs and minor arcs gives you the unit interval. But this method was first introduced in the 1918 paper by Hardy and Ramanujan about partitions, and there this terminology made more sense. Sorry, it's there.
I think you are doing wrong.
Sorry?
Someone just joined and I think he was on mute. So, but now he's muted.
Okay. Yeah, so yeah, you divide this integral into major arcs and minor arcs, and the union of major arcs and minor arcs gives you the unit interval. Okay. In literature, sometimes this method is also referred to as the Hardy-Littlewood method, because they were pioneers in using this method. But sorry. Okay, I'll just continue. If there's a question, maybe let me know. But because of like if you're a stickler, you should probably call it Ramanujan, Hardy-Littlewood. and Vinogradov method. And in fact, the modern formulation of this method is by Vinogradov. Okay, so what are these major arcs and minor arcs? The idea of major arcs is that you want your alpha to be close to a rational number a over q with small denominator q. And in this situation, you have a more or less precise control over the value of S alpha. S alpha is the exponential sum. And so in this case, we have an asymptotic estimate for alpha. And we can evaluate S alpha fairly precise. And so this situation corresponds to the major arcs, and the complement of major arcs corresponding to the unit relative to the unit interval are referred to as the minor arcs. So we choose a parameter p, which is less than n power delta, where delta is some fixed positive small number, and we define the major arcs as the set of alpha for which there exists a, which is an integer, and q, which is a positive integer. And by small denominator, we mean that q is less than or equal to this parameter p. And by close to a rational number, we mean that the distance from alpha to a by q is less than p over qn. Note that because of Diophantine, because of Dirichlet's approximation theorem, you can do this for all numbers alpha. It's just that it need not necessarily be that the denominator is small enough. Yeah, and as I said earlier, the complement of major arcs relative to the unit interval are the minor arcs. Generally, what you would expect is that the major arcs will give you the main term, and the minor arcs will give you the error term, which is hopefully smaller than the main term. Sometimes the situation may not work out that way. So, for example, in binary Goldbach, we don't necessarily have this, and that's why the circle method, we haven't been able to use the circle method to prove the binary Goldbach conjecture. But for example, in ternary Goldbach, you can make the contribution of, you can prove that the contribution from major arcs is more than the contribution from minor arcs. And when things work well enough, you can prove, you can use the circle method to prove these kind of results. Right. Yeah, also another thing to note is that because in the case of minor arcs, we do not have precise control over the value of S alpha, what we hope for is to get upper bounds on the integral over the minor arcs. So we'll get to that soon enough. But so if the binary Goldbach, if we are not able to apply by the circle method to binary Goldbach, what are we doing here? And the answer is that there is an almost Goldbach version, which was proven by Linnik. So in early 1950s, Linnik proved that there is an absolute constant k, such that every sufficiently large even number n can be written as the sum of two primes and k powers of 2. So yeah, so just before that, so he proved this in 2 papers. The first paper was conditional on the generalized Riemann hypothesis, and the second paper he proved this in.
My squirrel got hit in the ass by a mad scientist. You're all I got. Big.
Could you pay me in advance?
Okay. Can you mute this? Yeah. Okay. Thank you. Right. So in the first paper, he proved assuming the generalized Riemann hypothesis. So quite a few of you might know what GRH is, but for those of you who don't know, so you have the standard Riemann hypothesis, perhaps the most famous unsolved problem, and the Riemann hypothesis is basically about the non-trivial zeros of the Riemann-Seed function, and it says that all the non-trivial zeros lie on the critical line, which is real part of S equal to half. So if you look at the series representation in real part of S greater than 1 of the Riemann-Seed function, it is 1 over n power s. So if you replace the numerator 1 in this case by the value of a Dirichlet character at that point, so and the Dirichlet character is denoted by chi. So if you replace it by chi of n, then you get a Dirichlet L series. And then if you take the complex analytic continuation of this, you get the Dirichlet L function. And Dirichlet characters, as some of you might recall, is this completely multiplicative arithmetic function that is associated with the group of units, with the units of the ring Z by Kz. This proof by Linnik was ineffective in the sense that it did not give a specific value of k. But then later on, people gave a specific value and made it explicit. So k is equal to, also just to note, the binary Goldbach conjecture would correspond to the case k equal to 0. Right, and so Liu and Wang in '98 proved k is equal to 50/1000. There have been many more developments since then, but here we'll only state those results which are relevant to us currently for this presentation. So Heath, Brown, and Kushta in 2002 proved k is equal to 13. So you can write any sufficiently large even number as a sum of 2 primes, and at most 13 powers of 2. And under GRH, they proved that you can take k equal to 7. And recently, Pins and Russa, just a few months ago, they proved that you can take k equal to 8 unconditionally. And in an earlier paper, they had also proved that you can take k equal to 7 under GRH. And the method that we are going to show now, that is going to be using the method pursued by Heath, Brown, and Kushta in the 2000 paper. Okay, so the strategy here is that you have S alpha as before. It's the sum over P alpha P. And then you have this other term P alpha, because you also need to take into account the powers of 2. So you have that additional term. And T alpha is runs over V from 1 to L, where L is the largest possible exponent of 2 for the number n. And here, instead of going from S alpha, instead of going from 2 to n, we take primes from omega n to n, where omega is a small positive constant. This is for technical reasons. It doesn't change the result too much. Omega is a very small positive constant, and it doesn't really matter too much. Right. So then, the number of representations in the range under consideration of an even integer would be equal to the integral from 0 to 1 S alpha square T alpha power k P minus n alpha D alpha as before. And then this, as before, we divide this integral into major arcs and minor arcs. Now, the major arc situation is fairly standard. So what we try and do in most cases is since we do not have much control over S alpha in the minor arc situation, we try to get an upper bound on the modulus of this integral, on the absolute value of this integral. And then we try to get a lower bound on the contribution from major arcs. And if the lower bound from the contribution of major arcs is greater than the upper bound on the modulus of the minor arcs, the integral over minor arcs, then we know that Rn has to be greater than 0. And then we have proved our result. And in general, the analysis of minor arcs is standard, but the analysis of major arcs is standard, sorry. But the analysis of minor arcs is unique to every problem. And in that respect, it reminds me of this line from Anna Karenina, that all happy families are alike, but each unhappy family is unhappy in its own way. And so, like, all major arcs are alike, but each minor arc is problematic in its own way. So we'll start with estimating the contribution of minor arcs. Can I just know how much time I have? So,
you still have 15, 17 minutes.
Okay. Right. So yeah, let me start with minor arcs. As I said, we want to bound the modulus of the integral over minor arcs, and by triangle inequality, we take the modulus sign inside. And the trivial estimates for S alpha and T alpha. So each of the terms in the exponential sum has absolute value less than 1. So S alpha has to be big O of n, and T alpha has to be big O of L. To do slightly better, so these are trivial estimates. To do slightly better, we'll define a set A lambda such that the value of T alpha, the modulus of T alpha, is greater than lambda L, where lambda is some small number between 0 to 1. And then we can split the integral over minor arcs into two parts. The first one corresponds to points which are in the minor arcs, as well as in A lambda. And the second corresponds to the points which are in the minor arcs, but not in A lambda. And for the second integral, we know that T alpha has to be less than lambda L. So we use that upper bound. And for the first integral, we use the trivial estimate for T alpha. And then the only thing left is to have an estimate for S alpha to find out the overall minor arc contribution. So the first case is minor arcs, a point which lies in the minor arcs and also in A lambda. And in this case, as I said, we use the trivial estimate, which is that T alpha is big of L. So you have L power K, and you have S alpha squared and measure of A lambda. And the size of this set A lambda is bounded by n power minus E lambda. Also, this less than sign just means big O of something. So if F is big O of G, it means that F is less than or equal to some constant times G. And sometimes it's more convenient to use less than instead of big O. So we have this result about the size of A lambda. And the proof of this lemma comes from probability theory. I'm not, admittedly, I'm not aware of the exact methods, something to do with martingale methods and stuff. But you see that you have two estimates for two different kinds of lambda. So E 0.722428 is greater than half, and E 0.863665 is greater than 109 by 1 over 154. And the reason for that is that you have two different lambdas, depending on whether you are assuming GRH or not. If you assume GRH, then you can do better. But if you don't assume GRH, then you have a different lambda. And so using this estimate on the size of A lambda, we can estimate the contribution from minor arcs intersection A lambda. And then the second case, where we estimate the contribution from the integral over minor arcs minus A lambda. As I said earlier, here we use the estimate T alpha is less than lambda L. And then the integral which is left is the integral over minor arcs S alpha T alpha squared. And we also have an estimate for this integral S alpha T alpha squared. And the way we get this estimate for over minor arcs is that we try to lower bound this integral in the interval 0 to 1. And then we try to upper bound this integral over the major arcs, because in the major arc situation, we have much more control over S alpha. So we try to upper bound this integral in the case of major arcs. And then by subtracting the integral, the lower bound from 0 to 1, subtracting the contribution from major arcs from the integral over 0 to 1, we get an upper bound on the contribution over minor arcs. And then using that, we have an estimate for the integral over minor arcs minus A lambda. Finally, the bound on S alpha. So for that, we use this theorem. It's sort of standard. You can find it in Vaughan's book on Hardy Littlewood method. And we have an estimate for E alpha P log P. We do not have an estimate so right now. So far in the presentation, we haven't seen an estimate for S alpha directly. So this is in the case Q less than or equal to N. Which is in general true. So to get an estimate for S alpha from this, we use something called partial summation. So it's a standard technique in analytic number theory, where if you have the sum over the product of two quantities, and if you know, if you have an estimate for the sum over one of those quantities, then you can use that, and you can use the fact that the other quantity is a function which is well behaved, it satisfies certain continuity properties and stuff. So you can use that to get an estimate over the sum of the product of those two quantities. So to get an estimate for E alpha P here, sum over E alpha P here, we write it as E alpha P log P times 1 over log P. And then we use the estimate over of the sum over E alpha P log P. And then the other quantity that is left is 1 over log P. And since 1 over log X is well-behaved enough function, so we can apply partial summation to get a bound on S alpha. So using that, we get a bound on S alpha. And remember that alpha is in minor arcs. So that means that the denominator is not small. And so the denominator is greater than the parameter. That is, Q is greater than P. And Q has to be less than N by P. And so S alpha, we have this bound on S alpha. And then we choose an appropriate value of P, which just, so P is equal to N power delta. So N delta is a small positive number. So choosing an appropriate value of P, we get this bound on S alpha, which is N power theta plus little o of 1. Little o of 1, as you may recall. So if you write F is equal to little o of G, it means that F is less than or equal to epsilon G for any positive epsilon greater than, so for any positive epsilon. Or in other words, if you take the limit F over G, this limit goes to 0. And in this case, theta can be taken 263 by 308 in general, and 3 over 4 under GRH. Again, when you assume GRH, you can do better. And so finally, combining all the contributions, we have an upper bound on the contribution from minor arcs. And once we have this upper bound on the contribution from minor arcs, we now want to compare this with the lower bound on the contribution from major arcs. And if the lower bound is greater than if the lower bound on the contribution from major arcs is greater than the upper bound on the contribution from minor arcs, then we know that Rn has to be greater than 0. And so we'll soon see the major arc situation. But for an appropriate choice of P and K greater than 7, the integral over minor arcs is indeed greater than the integral over major arcs is indeed greater than the integral over minor arcs for large enough n. Note that the order of the estimate is the same. Both are of the order n times L power k minus 2. So it's really in the constants. We need to adjust the constants properly so that we can prove that one is greater than the other. Sarda, can you tell me how much time do I have?
Yes, you have 10 minutes.
Okay. Yeah, so I'll go through this a bit more quickly, maybe just highlight the important points here. So to estimate the major arcs contribution now, instead of looking at the original integral over major arcs S alpha square T alpha power k E minus alpha n, we first just estimate S alpha square E minus alpha n. And here n is lowercase n, it's not capital N. And so we are estimating this for any general n. And then we'll show how to convert, how to use this estimate to get an estimate for the original integral over major arcs. So you have this result that the integral over major arcs of S alpha square E minus alpha n d alpha is Jn In plus big O of n by phi n, where phi n is the Euler-Gaussian function, times Sn plus some other error terms. So Jn In is really the one that's giving you the main term here. And then you have to show that the error, the other error terms are small enough. The reason why I haven't mentioned the other error terms is because they get absorbed in this first error term, which is big O of n by phi n Sn. And Sn is a fairly complicated sum over primitive characters. The characters are such that they are not both principal, and they have moduli r dash, and the least common multiple of this moduli of the two moduli is n, and that has to be less than the parameter p. We'll also look at Jn In very soon. So Jn is generally called the singular integral, and In is called singular series, and they occur in all kinds of, in every problem where you use a certain method. The term singular, the singular series and singular integral appear, and that's why I said the analysis for major arcs is fairly standard. Right, and so now you have an estimate for Sn, and basically you have two terms. So in the first term, you see that I've mentioned that two characters, chi dash, which belong to the set of characters b eta. B eta is basically a set of characters which have so the L function corresponding to these characters is such that there is a 0 in a certain region, and so there is at least 1 0 in that region, and all those characters that satisfy that property are in B eta, and the region is depends on this parameter eta, which is less than log n. So this is the reason why assuming GRH or not assuming GRH is important. Because if you assume GRH, then the zero-free region is everything except the critical line. But if you do not assume GRH, then you have to use zero density estimates and that kind of stuff. And then those estimates vary slightly. So now we need to convert this into our original integral. We need to use this estimate to get an estimate for our original integral, which is on S alpha square D alpha power K E minus alpha N, where this is a capital N. And the way we do that is we sum this integral over all values N equal to capital N minus sum of powers of 2. So this is a sort of neat trick to use our estimate for integral S alpha square E minus alpha N for our original integral. And then you use the upper bound on Sn. So Sn, the upper bound on Sn had 2 terms, and those contribute the 2 error terms in the major arc integral. And the first term is our main term, which is sigma naught. So sigma naught, as I said, so the main term in case of S alpha squared E minus alpha N was J and In. So sigma naught would be just a sum over that main term over all all valid values of N. And then sigma 1 is sum over N by phi N. Phi N again is the torsion function. And sigma 2 is also something similar. So to bound sigma 1, we use the fact that N by phi N, N over phi N is less than product of 1 plus 1 over P. And for this, we just use the standard formula for Euler torsion function, which is N times product 1 minus 1 by P, 1 over P. And then this product can be written in terms of the Mobius function. So mu square Q is 1 if Q is square free and 0 otherwise. So writing this in this form yields a bound on sigma 1, which is log n power k. And similarly, you bound sigma 2, and this gives you log n power k times log n minus 1 by 1 over 12. And finally, the main term. So Jn, as I said, is the singular integral. This is written as a sum, but it can also be written as an integral. And it's 1 over log m1 log m2, where m1 plus m2 equal to n. And In is this product depending on primes. And this product should remind you of the twin prime constant. So in fact, we will write In in terms of the twin prime constant. And so then we have a simple bound on Jn, where instead of log 1 over log n1 log n2, you replace it by log n 1 over log n squared. And then you just count the number of m1, m2s such that m1 plus m2 is n. And then because you there is some inefficiency in that estimate, you have an error term. And this error term will also get added along with multiplication by In. So the error term in sigma naught will be given by the error term in Jn multiplied by this estimate of In, which is log n. Note that we want a lower bound on the main term, but here we are including the upper bound on In just because we want to estimate the error in the main term, and we want to show that the error is small. So that's why in the main term we have still retained In. We haven't used that estimate yet. And then we write in terms of the twin prime constant. And using that, we obtain a lower bound on sigma naught, which is our main term, and providing that k greater than 7 when, and here we are assuming GRH, and combining the estimates for the main term and the other terms, we get the earlier stated result for the integral over major arcs. So I can end my presentation here, or I can describe other problems which are of similar kind. How much time do I have, Sarabhi?
Theoretically, it's the time now, but if
okay, then
it's a matter of 1 minute or two, you can describe some other problems if you want.
Yeah, so I mean, I just wanted to mention that the circle method is applicable in a variety of problems. So Waring's problem is a standard example. Waring conjectured that in every natural number k greater than 2, for every natural number k greater than 2, we should be able to write every natural number as a sum of at most s kth powers of natural numbers. So, for example, 25 can be written as 3 squared plus 4 squared. And so what's the minimum number of terms that you need to represent the number as sum of squares or sum of cubes or something like that? And in this case, so it was first proved by Hilbert using combinatorial methods, but the circle method gives you better estimates of this value of s. And the least possible value of s for a certain k is denoted as little gk. But more often than not, it's more interesting to consider the problem of representing a sufficiently large n as a sum of s kth powers, because sometimes smaller numbers could be exceptional cases, and they could inflate the value of little gk. And so the least possible value of s for sufficiently large n is denoted as capital GK. And then you can combine Waring's problem with the Goldbach problem. So instead of saying sum of kth powers of natural numbers, you can say sum of kth powers of primes. Or you can, in the Linnik Goldbach problem, you can, instead of using the powers of 2, you can have powers of 3 or 4 or some other number. And then you can, if you want, you can also combine all 3 of them. You have Linnik Waring Goldbach problems where you have some powers of primes and then some powers of 2 or something else. So all of these problems can be tackled using the circle method. Thank you. That's it from my side.
Okay. Thank you very much, Shehzad. And well, let's give a virtual round of applause to the speaker, please.
Thank you.
And yeah, okay. And if there are any questions, please feel free to ask.
Hi, so I do have one question.
Hi.
Maybe it's not very important, but at some point you were explaining about this constant K, and you say that under GHS or something like this.
GRH, yeah.
Yeah, what's that? Maybe I didn't hear it. But...
Yeah. So GRH is generalized Riemann hypothesis. I sort of tried to explain it in a couple of lines. So are you aware of the Riemann hypothesis?
Yeah.
Yeah, so the Riemann hypothesis basically says that the zeros of the Riemann seed function, the non-trivial zeros, lie on the critical line. And the critical line is real part of S equal to half. So the generalized Riemann hypothesis says that if you have a Dirichlet L function instead of Riemann seed function, then even the zeros, non-trivial zeros of the Dirichlet L function lie on this critical line. And the way a Dirichlet L function is defined is using Dirichlet characters. So yeah, it basically says something about the zeros of Dirichlet L functions, which are kind of more general than the Riemann seed function. And also, you could think that maybe GRH is probably even more difficult than.
Okay, so it's not uncommon to take it as an hypothesis, or?
Yeah, it's not uncommon at all. In analytic number theory, Riemann hypothesis and generalized Riemann hypothesis are assumed very often.
Thanks.
Yeah, thank you.
Any more questions?
Yeah, I wanted to ask you something. At some point, you speak about a function capital E of lambda.
Yes.
And that it has a relation with probability, you say?
Yes, and
can you say
I thought you might be interested in this. Yeah, so what we want to do is, I'll go back to this one. So what we want to do is, you want better estimates for S alpha and T alpha. And the way to do that would be to define a set where T alpha is greater than lambda L. And then you divide the integral over minor arcs into two parts, where you consider alpha in A lambda and you consider alpha which are not in A lambda. And when alpha is not in A lambda, you can use the estimate T alpha is less than lambda L. And when alpha is in A lambda, you can have the estimate T alpha is greater than lambda L. So in this case, we need to estimate the size of A lambda, the size of the set A lambda. And that's where probability theory is used. I think in the paper it's mentioned like methods, martingale methods for exponential inequalities. But as I said, I do not know much about probability theory. Maybe you have a better idea of what this means. But it's basically you want to estimate the size of A lambda.
Okay.
Set A lambda.
And they use martingales for estimating that.
Yes, apparently, yes. The
that
original
sounds,
authors.
interesting.
Yeah, so the paper was written by Heath Brown and Bushra, and they also had used some other method initially, but then Professor Keith Bell, told them that it can be done much more easily using probability theory, and so that's the method that they've given in the paper. But yeah, it's not something that's it's not something that people will know in analytic number theory.
Okay, thank you.
Yeah, no problem. Thank you.
Are there more questions? If not, let's all thank the speaker again in a warm virtual whatever we can do. And okay, thank you very much, Shehzad, for having come
thank you.
to Barcelona, at least in
virtually. Yeah,
like virtually, exactly.
Yeah. Would like to visit it someday. Visit those buildings again by Gaudi.
Yeah.
Thank you.
Okay.
Bye.
Thank you. Bye.
Bye.